This video will run through exploring and travelling problems for the networks and decision mathematics component of Further Maths. So what we're talking about in this section is describing journeys. And so a journey for an undirected graph is a way of describing the movement through or around a graph. It's usually noted as a series of vertices through which you pass. And this series of vertices is called a route. So often we'll talk about the route, for example, in the diagram here from the office to the gymnasium. And so there would be various journeys that you could take, and we would be noting what vertices or what locations we are passing through on that journey. So a journey can actually fall into one of 5 different categories. We can have a walk, a trail, a path, a cycle, or a circuit. Each of those types of journeys has a specific criteria that we're going to have a look at now, and it can be also really useful to have a summary table to help you identify what are the key features and the absolute musts and the absolute must not for each of those types of journeys. The first of our journeys is a walk. So a walk is the most basic style. There's no restriction on the start and finish location. We're allowed to repeat edges, we're allowed to repeat vertices, we can include as many or as few as we'd like. So an example of a walk, as we said, might be going from the office to the gymnasium. And so I might, from the office, walk just straight there. Or another version might be that I go via the library and the computer room to the gymnasium. Or I might go to the library, go to the maths classroom, and then realise I forgot something from my office, so I go back, go to library again, computer room, and gymnasium. So there is no restriction there. Obviously, highlighting it on the graph only works if you visit each place once, and so that's why it can be important to actually note down your journey. And usually your vertices will be labelled just with a single capital letter, or you may choose to abbreviate so that you can state that journey. So if I went from the office to the library, to the computer room, to the gym, I might note it like that. Similarly, if I went to the library and the maths classroom, back to my office, to the library again, computer room, and gym. So that means that anyone looking at this now can understand the journey or the walk that was taken in this case. The first type of journey where we start to see some restrictions is a trail. So a trail is a journey where no repeated edges occur. I must start and finish in different locations, and that's another condition here. And I can use vertices more than once though. So in this case, maybe I have started the mathematics classroom, I've gone to the science lab, to the office, to the computer room, library, back to maths, and then the gym. So that would be and haven't repeated any edges. So to write out that trail, we had maths, then to the science, office, computer room, library, back to maths, and finally finishing at the gym. The next journey that we're looking at is a path, and so we're stepping up our restrictions again. So with a path, there's no repeated edges or vertices, and we must start and finish at different locations. So again, we don't have to use everything. I may be in the computer room, go to the office, to the maths classroom, and then finish at the science lab, and that would be an example of a path. And so again, listing my journey, simply loading that down there. The next 2 journeys that we're looking at have a common feature where we must start and finish at the same location or the same vertex. So a circuit is a special type of journey with no repeated edges. So again, the vertices can be used more than once, but we definitely cannot repeat edges. And I have to start and finish in the same location. So for this one, I might go from the library to the maths classroom, to science, to the office, and back to the library. So you can see here, I've now got a closed loop. And so again, if I'm noting them down, library, math, science, office, and back to the library. I should be noting that the start and the finish vertex are the same and nothing is repeated in the middle there, no combination of repeats. And we do have that closed off loop. So that's our circuit. Our second type is called a cycle. So here, again, we start and finish in the same location, but this time there's no repeated edges or vertices. So I can't pass back through the same location more than once. And so I might say that my circuit, or a cycle, sorry, is an example of gym to maths to science to the office, library, computer, and back to the gymnasium. So again, I'm not repeating anything there, and starting where I finished or finishing where I started. Okay, so again, when you write it down, you're noting your start and finish vertex are the same, and this time there should be absolutely no repeat in that middle section rather than just a combination of edges. And so as I said, it can be really useful to have a summary. I would usually have this summary maybe with some additional information annotated on the side as well, but it will just help you as a quick reference to go, if they've mentioned one of these key types of journeys within the body of a question, that you can have a quick reference guide to see, well, what are the conditions that relate to that type of journey. And vice versa, if you are told about particular conditions and asked to identify what would be a suitable journey that is talking about, you've then got those keywords that you can draw from. Building on our basic definitions of journeys, we then have two categories of special journeys. So in the basic style, in the definitions we've looked at previously, there's no requirement for you to use every edge or every vertex. There are restrictions on what you can and can't repeat, but you don't have to use everything in the graph. However, with these two special categories, we do have that requirement. So Eulerian trails and circuits require you to use every edge in the journey that you are describing. Okay, so remember, a trail will start and finish in different locations, whereas a circuit will start and finish in the same location. And these ones require every edge. The Hamiltonian paths and cycles require you to use every vertex in your path or in your journey. And so a Hamiltonian path will start and finish in different locations. Hamiltonian cycle will start and finish in the same location. So we're going to have a look at some examples and some little hints and tips for each of those now. Starting off with the Eulerian Trail. So as we said, a Eulerian Trail must include every edge. In order to know whether a Eulerian Trail exists or not, instead of sitting and sort of tracing our way around the graph and trying to figure out what is the combination and pathway, there's a couple of things you can check to begin with. The first thing, that a Eulerian trail is only possible if the graph has two vertices of an odd degree. Not three vertices, not one, not none, it has to be exactly two. So if we look at vertex A, and we just isolate that, we can see A has two exits coming out of that. So we would just say that A has a degree of 2. B has a degree of 3. C has a degree of 3. D has a degree of 4. And E has a degree of 2. And so from that, I can see that B and C are vertices that have an odd degree. The reason why that is useful is that the odd degree will be the start and the finish point. So I know that if I start at vertex C, I will be able to firstly, yes, create a Eulerian trail, but then secondly, I know that my finish point will be vertex B. So let's have a go. If I start at C, I can go across to D, I can come back around, I can go up to B, D, E, A, and B. So I was able to trace my way around the graph without lifting my pen. I only covered each edge once, so there was no repeated edges. And I started at C, finished at B, so different locations. And so again, we would want to write out our graph like we were before, or sorry, our journey as we were before. And so we're just listing those combination of pathways that we went across, okay, or through the vertices to get us to each of those locations and across each of those edges. Okay, there are multiple answers in a lot of cases when you're looking at Eulerian trails. Obviously, I can do the exact same journey in reverse, starting at B and ending at C, and there would be different combinations potentially possible as well. So looking at an example now of a past exam question, the suburb of Aluma has a skateboard park with 7 ramps. The ramps are shown as the vertices T, U, V, W, X, Y, and Z on the graph below. Nathan begins skating at ramp W and follows a Eulerian Trail. At which ramp does Nathan finish? So in this question, you're expected to know when you see that Eulerian Trail that it is one where every edge is used just once. You will have a different finish point as to the start point. And the little hint about how you can utilise the degree of the vertices means instead of trying to find the pathway through and figuring out where Nathan can finish, all we need to do is actually work out the degree of the vertices. So if we start here, we've got T has a degree of 2, U has a degree of 4, V has a degree of 3, W has a degree of 3, X has a degree of 2, Z has a degree of 4, and Y has a degree of 4. So knowing that for a Eulerian trail, if we start at one odd vertex, we must finish at the second odd vertex, means Nathan must finish at ramp V. So he finishes at ramp V. That's without even doing any checking of what the trail would be. We just need to identify the other odd vertex so that we can identify his finish point. This second example is another really common style of question. So we're told for this graph, a Eulerian trail currently does not exist. For it to exist, what is the minimum number of extra edges that we would require? So we need to add some edges to the network. And so again, this is pointing you towards identifying odd vertices. So first I'm going to go through and just check all of the degrees of the vertices. So A has a degree of 3, B has a degree of 3, C has a degree of 2, D has a degree of 5, E has a degree of 3, F has a degree of 4, G has a degree of 3, H degree of 2, I degree of 3, and J degree of 2. So at the moment we have 1, 2, 3, 4, 5, 6 vertices that have an odd degree. In order to have an Eulerian trail, we can only have 2 odd vertices. At the moment, we've got way too many. If I was to add an additional edge between B and A, what that does is all of a sudden A now has a degree of 4, so it makes it even, and B also now has a degree of 4. So by adding an edge between 2 odd vertices, I make them both even. Following on from that, I can then also add an edge between E and I. And so again, makes both of those now even vertices. So I'm left with just the 2 odd vertices, which allow me to have a Eulerian trail. So here, the answer to the question, the minimum number of edges, I would need to add 2 edges to this graph. The thing to remember is for every 2 odd vertices, you want to add 1 edge. Okay, so by adding one edge, you will get rid of or eliminate two odd vertices out of the graph. So you'll often see questions like this, and that's a really nice, easy hint or something to have written down so that you can refer to. Moving on now to the Eulerian circuits. So Eulerian circuit is a circuit that must include every edge. So with Eulerian, we must use every edge. With a circuit, we start and finish in the same place. So same start and finish vertex, and we repeat no edges. Okay, so every edge once and start and finish in the same place. Now this is only possible if all of our vertices are even. So my first thing that I want to do before I even think about finding what the circuit is I'm going to check the degree of the vertices. So if I start with A, I've got a degree of 2, B has a degree of 4, C, degree of 2, D, degree of 4, E, degree of 4, and F, degree of 2. So once I've established that, yes, a circuit, a Eulerian circuit will exist, I can then think about finding out a possible answer. Now, in this case, there will be multiple possible answers. So, for instance, I could start at F, go to D, C, B, A, E, B, D, E, F. So again, I didn't lift my pen off the page. I was able to trace every edge on the graph without any repeats, and I started and finished at the same location of F. Again, if we were to write that out, I can remember the pathway that I followed. I'm just simply noting down my vertices that I travelled through to get me all the way around the graph. So you will see repeated vertices throughout, but no combinations of. So that means AB is not shown twice, okay? And remember, your start point and your finish point must be the same vertex. So an example for a Eulerian circuit. Parcel deliveries are made between 5 nearby towns P to T. The roads connecting these 5 towns are shown on the graph. A road inspector will leave from town P to check all of the roads and return to town P when the inspection is complete. How many roads will the inspector have to travel on more than once? So this is similar to the previous example with the Eulerian paths that we looked at, in that we want to check the degrees of our vertices, and instead of adding edges to the graph to make a circuit possible, we're looking at which edges would we need to repeat. So effectively, we're adding an additional edge between any odd vertices. So firstly, let's check the degree. So P has a degree of 3, Q has a degree of 3, R has a degree of 4, S has a degree of 3, and T has a degree of 3. So we know that in order for there to be a circuit, that we need to have all even degrees. So if I was to travel starting at P, I could travel to Q, to T, to R, P, S, T. Now I'm not going to be able to complete my journey that's required. So if instead I add additional edges, which will represent the connections that I travel on twice, I will be able to create a scenario where all of the vertices are even, and therefore I know a circuit is available. So if I join P and Q, they then become even. And if I join S and T, that also becomes both even. And so now I know I will be able to complete a Eulerian circuit, and the edges, or I guess the roads that I will travel on twice, are the connection between P and Q and the connection between S and T. So there will be 2 roads, and we'll just note between P and Q and S and T. Our second type of special journey, so looking now at our Hamiltonian path. So a Hamiltonian path, as we said, is one that must include every vertex. So Eulerian for edges, Hamiltonian for vertices. So in this case, we cannot repeat any vertices, we cannot repeat any edges. However, you do not have to use every edge in the graph. In this case, we are also starting and finishing at different locations. Now, unfortunately, with Hamiltonian, there isn't a quick little check that we can do at the beginning with a degree of vertices like there is for the Eulerian. So with this one, we just have to jump in and see what we can create. So if I was to start at F, I could travel to E, D, C, B, and A, and I formed their Hamiltonian path. Remember, at every vertex, so each letter is represented just once, and I'm starting and finishing at different locations. Looking at an example now, so we're back to the suburb of Aluma with the skate park. Zoe begins skating at ramp X and follows a Hamiltonian path. The path she chooses does not include the two rough tracks. Write down a path that Zoe could take from start to finish. So remember, she's starting at X, and we're not including these two rough paths or edges there. And so again, just starting at X and working our way through that she has to visit every ramp or every location. So we've got to be careful because she can't use those rough paths. So we can come through to U, V, and W. So again, there are multiple answers here. She could also travel from Z to W and up to V, but the pathway that I've gone is X, Y, T, U, Z, V, and W. Again, checking, no vertex is repeated, all of them are included, and you've started and finished at different locations. The final one we're looking at now is a Hamiltonian cycle. So Hamiltonian cycle includes every vertex, and we must start and finish at the same vertex. So again, no repeated edges, no repeated vertices. You do not have to use every edge. And there is one little hint that you can look at. So when you look at a graph, if you have a vertex that has a degree of 1, so if we had an additional edge and vertex here that had a degree of 1, I can tell you that a Hamiltonian cycle cannot exist here because I would be unable to get to F and then back out again to another location. So that is one nice little hint. Not as good as what we can check with our Eulerian trails and circuits though. So let's have a look at a couple of examples now. And so our first one here, a zoo has an entrance, a cafe, and 9 animal exhibits: bears, elephants, giraffes, lions, monkeys, penguins, seals, tigers, and zebras. Freddie is a visitor to the zoo. He wishes to visit the cafe and each animal exhibit just once, and he wants to start and end at the entrance. So the first question is, what is the mathematical term used to describe this route? So when you get a question like this, you have to be really specific. So here he is visiting the cafe, every exhibit, and starting and finishing at the entrance. So that means he is visiting every vertex in this graph. And so that means we have a Hamiltonian cycle. So I've got the wrong label there, sorry. Then for part B, draw one possible route that Freddie may take on this graph. So remembering he has to start and finish at the entrance. That's where we need to go. And we want to have a look and see what are the little things that we might need to avoid and be careful of. So if I left the entrance, if I went to the lions, the giraffes, tigers, the monkeys, I got the cafe, the elephants, the bears, the seals, down to the zebras, penguins, and then back to the entrance again. So there I've visited every vertex. I didn't have to lift my pen to get there. And I started and finished at the beginning. So again, this has asked us to draw on the graph. If we had to list, we could just simply say the entrance, lions, giraffes, tigers, monkeys, the cafe, elephants, bears, seals, zebras, penguins, and back to the entrance again. For our final example, we're back to the suburb of Aluma and the skate park. So Bria can skate over any of the tracks, including the rough track. He begins skating at ramp X and will complete a Hamiltonian cycle. How many ways could he do this? So firstly, we need to identify one possible Hamiltonian cycle, beginning and finishing at vertex X. And then we can think about, were there any other options? So if I leave X and go to Y, T, U, Z, V, W, back to X. That gives me one possible pathway. And so with these ones, I would want to be writing down what my pathway is so I can keep a track of what I've done. And so obviously, really quickly, a second possible pathway would be the exact same, but in reverse. So X, W, V, Z, U, T, Y, and back to X again. But potentially when I came through here from U, I may have had a couple of options. So I could have come X, Y, T, U, cross to V, Z, W, and the rough. So there's a whole new path. So X, Y, T, U, but then across to V, Z, W, X, and again, the reverse of that. So X, W, Z, V, U, T, Y, X. So I'm now up to 4 possible pathways. And then I need to consider, was there something else? Remembering that it has to fit the definition of our Hamiltonian cycle. So I have to finish back at X again. And I really only have these 2 options here from leaving U. And so that gives me confidence to say that I have achieved both of the possible moving, I guess, forward pathways, and then the opposite of those coming back in the reverse. So that leads me to say there are 4 ways that Vera could do this journey that's required. So again, here's a bit of a summary of your Eulerian and Hamiltonian types of journeys. And again, you may wish to add a little bit more information around that. Put as much of sort of the key things that you might need there. It's really good to have all of this in one space on a summary so that you've got that quick reference. And the examples that we've gone through are just a bit of a snapshot of the types of things that you might be asked. It's not often that they explicitly tell you the type of journey that you need to create. More often than not, they're giving you information about it so that it has to cover every road, which is represented by the edges, or you have to visit every landmark, which are represented by the vertices. So picking up on those key things and then being able to filter down and identify the type of journey that you're required to identify can be really helpful. Okay, I hope that was useful, and I'll see you next time.